Imagine an AI that learns to see, not by copying a smarter computer's homework, but by listening to humans describe the world for 90 seconds straight. Today, we're looking at the model that proves you don't need secrets to build state-of-the-art vision. Welcome to our podcast, Artificial Intelligence, Papers and Concepts, curated by Dr. Satya Malik. Just a quick heads up before we dive into the nuts and bolts. I'm an AI-generated voice, and my co-host here is one as well.
That's right.
We are here to guide you through the latest research with a bit of synthetic charm.
It's a fascinating time to be an AI, discussing the architecture of other AIs.
It really is. And today we're tackling a paper that's making some serious waves. It's called Molmo and Pixmo, Open Weights and Open Data for State-of-the-Art Vision Language Models.
And it comes to us from the Allen Institute for AI, or AI2.
Right.
This paper, it's a significant line in the sand. The mission here was incredibly ambitious.
What were they trying to do?
AI2 set out to build a vision language model, a VLM, that could go toe-to-toe with the proprietary giants.
So we're talking about models like Claude 3.5 Sonnet, Gemini 1.5 Pro.
Exactly, and even GPT-4o. The heavy hitters.
Those are massive closed-source models. The training budgets alone must be astronomical.
They are. But AI2 wanted to beat them, or at least compete, entirely using open data and open weights.
So no black boxes. They wanted to show everyone exactly how the sausage is made.
That's the idea.
Okay, let's unpack that. Because usually when we hear open source in AI, especially for vision models, there's a bit of an asterisk, isn't there?
There is a big one. And that asterisk is a process called distillation.
Distillation.
It's really the status quo for most so-called open weight models right now, like the LV series.
It sounds kind of refined,
I
like
know.
making whiskey, but
Yeah.
I have a feeling it's a bit more derivative.
That's a very polite way to put it. Think of it like copying the smart kids' homework.
Knew it.
So here's how it usually works. Researchers take a huge data set of images.
Right.
But instead of paying humans to describe them, which is slow and super expensive, they just feed the images into a proprietary model.
Like GPT-4 Vision.
Exactly. They ask it, describe this image. Then they take that description, the output from GPT-4, and use that to train their own smaller, open model.
So the open model isn't learning to see the world from scratch.
No.
It's just learning to mimic how GPT-4 talks about what it sees.
Precisely. It's mimicking the output, not learning the underlying logic. And the consequence of that is, well, it's pretty severe for the scientific community.
Why that?
We end up missing the foundational knowledge of how to actually build these things from the ground up.
Right, because if OpenAI just turned off their servers tomorrow, the open community would hit a brick wall they wouldn't know how to improve.
Exactly. They've been dependent on the teacher's answer key this whole time. It creates a ceiling. You can rarely surpass the original if you're just copying.
And this is where Molmo comes in, I take it.
This is the Molmo promise. The researchers at AI2 built it from scratch. No synthetic data from proprietary VLMs.
None at all.
None. No GPT-4, no Claude. It is, and this is their phrase, state-of-the-art in its class of openness.
That is a bold claim. To say, we're not going to use the best tools available, we're going to do it the hard way. And still expect to win.
It is the hard way. But as we're about to see, it might just be the better way.
Before we get into exactly how they pulled that off, and I really want to talk about the clever microphone trick they used, we do need to pay some bills. This podcast is sponsored by BigVision.ai, a consulting and product development company that helps companies of all sizes build computer vision and AI solutions. You can reach them at contact@bigvision.ai. Okay, we're back. So Molmo isn't cheating. They're not copying homework. If they aren't using GPT-4 to describe images, what are they using?
They're using something called Pixmo.
Pixmo, as in pixels for Molmo.
You got it. And honestly, while the model architecture is solid, the data is the real breakthrough here. Pixmo is this whole collection of data sets they built just for this project.
So they had to go back to getting humans to describe images again. I feel like we've seen that movie before. It's expensive, it's slow.
And the results are often mediocre. It leads to what researchers call the captioning problem.
Which is what exactly?
Humans are efficiently lazy.
I feel seen.
Well, in data annotation, it's a huge issue. When you ask someone to type a description of an image, they're brief. They only focus on the most obvious thing, a cat on a mat.
True. Typing a whole paragraph is effort. If you're paid per image, you're typing cat and moving on.
Exactly. They don't mention the texture of the mat or the lighting in the room or the book on the table in the background. And that brevity, it just kills the model's ability to learn rich, detailed features.
So the researchers came up with a trick to get around this human laziness.
They did. They used a modality switching trick. They realized the bottleneck wasn't the human's ability to see,
It was the keyboard.
it was the keyboard.
Okay, this is where it gets really interesting. What did they do?
They didn't ask people to type, they asked them to speak.
Just talk about the picture.
Just talk. They showed annotators an image and said, give us a deeply detailed description, speaking into a microphone, for 60 to 90 seconds.
A minute and a half. That's a long time to talk about one photo.
It feels like an eternity, and that's the magic.
How so?
Because you run out of the obvious stuff in the first 10 seconds. It's a kitchen, there's a fridge, there's a stove.
And then the panic sets in.
Or the boredom. You've got 80 seconds of dead air to fill, so you have to start looking closer. You start describing details you'd normally ignore.
The fridge is stainless steel. There's a pineapple-shaped magnet on it. The counter has a marble finish with gray veins.
Exactly. So by changing the input method and enforcing a time limit, they completely bypass that laziness filter.
And the captions were much better.
Way better. This method, which they call PixMoCap, produced these super detailed captions, often over 200 words, and the annotators said it was less tiring than typing.
Because speaking is just more natural.
Right, and it also solves the cheating problem. They kept the audio receipts,
The recordings.
the recording, so they can prove it's a real human, not someone just reading output from GPT-4. It validates the whole process.
That is so clever. It's a human-centric solution.
It really is. But captions were only part of it. Dense descriptions tell you what's in the image, but not where things are.
Right. Knowing there's a pineapple magnet is one thing. Knowing which pixels are the pineapples another. Usually you'd use bounding boxes for that.
Correct. But drawing a type box around a bicycle or a potted plant is slow and tedious.
So what did they do? Let me guess. They made it simpler?
Much simpler. They switched to Pix More Points.
Pointing.
They simply asked annotators to point. Just click on the object, click on the pixels.
So way faster than drawing boxes.
So much faster. And because of that speed, they collected a massive amount of data. We're talking 2.3 million grounding annotations.
It's a huge number.
It is. And it teaches the model to ground its knowledge, to connect the word chair to the specific pixels of a chair. It's what makes it a true vision model.
Okay, so we have humans talking for descriptions and pointing for locations, but the paper says they did use some synthetic data. I thought you said no cheating.
No synthetic data from proprietary VLMs. Big difference. They used a really clever technique for documents and charts called PixMoDocs.
How do you make synthetic data for a chart without having an AI look at it first?
You generate it from the code up. Instead of asking an AI to describe a chart, they used a text-only LLM to write the code that creates the chart.
Oh, that's brilliant.
It is.
Because if you have the code, you already know the exact data values. You have perfect ground truth.
You got it. The code literally says value 52.4. There's no interpretation needed. The model just learns to map the visual representation back to the exact data.
It removes all the ambiguity. That's smart.
Yeah.
But my favorite part of this section has to be the clocks.
The Pixmo clocks dataset.
Please explain this, because it's hilarious that these super advanced AIs are terrible at reading analog. So
Both of the hands at different angles to, generalize the logic of telling time. They just hallucinate.
So Molmo decided to fix this.
They basically brute forced it. They created a synthetic data set of 826,000 clock images, different watch faces, different times, all generated by code.
That is a lot of clocks.
It is. And the result, Molmo is now dramatically better than the big proprietary models at reading clocks. It shows that if you find a blind spot, you can just code your way out of it.
So if I'm ever in an action movie with a ticking bomb, I want Molmo on my team.
Ideally, yes.
Okay, so we have this incredible data engine, Pixmo. What about the brain of the operation? The architecture itself?
Yeah.
Is it some radically new design?
It's actually surprisingly standard. They didn't try to reinvent the wheel. It's a vision encoder, like CLIP, connected to a standard large language model.
So the magic isn't in some new undiscovered neural network layer?
Not primarily, no. But they made some very smart tweaks. For one, they simplified the training pipeline. They trained the vision part, the language part, and the connector between them all at once.
Which is more efficient.
More efficient and less prone to weird errors. But you mentioned something in the paper, the multi-crop strategy. That's a really important detail.
It sounded complex. What does it do?
It's for high-resolution understanding. A standard vision encoder squashes an image down to a small square, maybe 336 by 336 pixels.
And you lose all the fine detail. Text becomes mush.
Exactly. So the common solution is to chop the image into tiles or crops. But Molmo uses an overlapping multi-crop strategy.
Like overlapping.
Well, think about an object that's right on the edge of a tile. It gets cut in half. The model loses context. By overlapping the crops, they make sure every part of the image is seen in its full context by at least one of the crops.
It's like a smooth pan instead of a jump cut.
Mhm.
It keeps things from getting severed by the grid lines.
That's a great way to put it. And this high resability leads to their other big aha moment,
Which is,
counting by pointing.
this goes back to the pixel points data, right?
It does. If you ask a normal AI how many apples are in this bowl, it basically just guesses based on the vibe of the image. Looks like 7.
And it's often wrong.
Very often. But Molmo, because it was trained on that pointing data, uses chain of thought counting. It points first.
It literally plots the coordinates.
It says, here's an apple, here's another, and then it gives you the final number.
It's actually counting one by one.
And the accuracy boost is huge. It grounds the answer in physical reality. It's verifying its own work as it goes.
So, the scorecard, all this clever data collection, the smart architecture, did it work? Did they actually beat the giants?
They really did. The largest model, Molmo 72B, it outperforms Claude 3.5 Sonnet and Gemini 1.5 Pro on academic benchmarks and on human evaluation.
That's huge.
And in human preference tests, where people just pick which answer they like better, Molmo ranks second only to GPT-4o. It beats almost everything else.
So it's sitting right there at the top of the leaderboard, surrounded by these multi-billion-dollar closed models.
And remember, there's a version of Molmo where everything is open. The data, the vision encoder, the language model, no black boxes at all.
That's the 100% open model. That's the dream for researchers, right?
It is. It proves you don't need to hide your recipe to cook the best meal. Anyone can inspect it, understand its biases, and build on it.
This feels like a turning point. For a while, it felt like the gap between open and closed source was just getting wider.
And that's why this matters so much.
Yeah.
Molmo provides a roadmap. It shows that the distillation trap, that reliance on copying the big guys, isn't necessary.
It democratizes the how-to manual.
Exactly. And it proves that rich, messy human input, like spoken voice, is still the gold standard. We haven't automated away the need for human perception. We've just found a better way to capture it.
That brings me to a thought I've been mulling over. The researchers found that just asking humans to talk instead of type revolutionized the data quality.
It's a powerful observation.
It just unleashed all this detail that was trapped behind the friction of a keyboard.
It suggests the bottleneck in AI isn't always the algorithm. Sometimes it's just the interface we use to teach it.
It really makes you wonder, what other human behaviors are we restricting by forcing them through keyboards? How much smarter could AI be if we let humans communicate more naturally, with gestures or voice or even eye movement?
That is the provocative question, isn't it? We design AI interfaces for computers, not for people. If we flip that and build data collection tools that fit natural human behavior, we might find the data we need has been there all along, just waiting for the right microphone.
A fascinating thought to end on. We want to thank you for joining us on this deep dive into Molmo and Pixmo.
It's been a pleasure.
If you enjoyed this deep dive, please make sure to subscribe to the podcast. We'll be back soon with more papers, more concepts, and hopefully more breakthroughs in the world of AI. Thanks for listening.